Hi. Today's topics will be run through again of the concepts of constraints in linear programming and how they're really represented, or how we use them to represent the constraints in FBA. Because even though we haven't talked about it too much so far, um, the formalism of each problem can be actually quite different, and they don't line up entirely. So there's a little bit of adaptation uh, necessary um, for FBA constraints really to be represented as the constraints in linear programming, and we're going to be talking through that and show how that's done today. And after we've gone through that, we're going to show how we can use this to add additional constraints to those that we've been using earlier to FBA, with the particular use case here being the concept of enzymatic constraints, or what we call molecular crowding, or cellular crowding, sorry. So, as a reminder to start this off, this here is the formalism behind linear programs. So, you'll have your objective vector, or first you'll have your variable vector. This is the state solution that you're trying to find. This is this x vector. And then you have an objective vector, which is the same format, and you want to maximize the product of the transpose of the objective vector multiplied by the variables vector, while satisfying these two constraints: that you have some matrix A multiplied by x less than or equal to b, and similar that each element of x is individually greater than 0. B here is a vector, while this 0 essentially represents the 0 vector, or just where, like 1 times n, where each element is positive. Now, if we look at the formalism for FBA, then we have the following. We have our metabolic map from which we can convert a stoichiometric matrix, and we have the steady state assumption that says that the stoichiometric matrix multiplied by the flux vector has to be 0. Additionally, we have internal flux constraints that the flux has to be between an upper and a lower bound, and similar for the exchange fluxes. Typically, these internal fluxes aren't too constrained. We're just going to add an upper and a lower bound to it for numerical reasons, but in basic FBA, you typically consider these to be mostly unconstrained. And then lastly, we have an objective function, which will typically be a single reaction, typically biomass, but there's always possibilities to change that. And that these objective coefficients multiplied by the flux vector have to be maximized. And now this looks sort of similar to linear programming at first glance, but there are some substantial differences if you look at it if you look at it more thoroughly. So let's start with the easy part. We can see this objective part, CT multiplied by x, is essentially the same. This actually fits quite well, where you might represent the C vector here as a 1 times n, or n times 1 instead of a 1 times n, so you don't have to transpose it, but that's really just a matter of choice of representation. There's not really any qualitative differences going on here. Then we can look here. Here we have this, but if we look at this stoichiometric constraint and try to shoehorn that into this ax less than or equal to b constraint, we see that they're not exactly the same. Because here the requirement is that ax is less than or equal to b, while here we have an equality constraint, and that they don't map neatly. If we were just set b 0, well, ax could still be negative, and that would correspond to this here, and that doesn't really fit what we're doing. And yeah, that will just not do. we're going to need to sort of find a way to actually convert this stoichiometric requirement into something that looks like this ax less than or equal to b. And then we also see here that these limitations on the individual fluxes, x greater than 0, isn't necessarily in line with what we'll see in a metabolic model, because in a metabolic model, often you will have reactions that are reversible. If you look at these internal flux constraints here, and exchange flux constraints here, we have nothing preventing us from alpha or psi or chi being negative. That's perfectly physiological and plausible and so on in every way, but it doesn't fit into this linear programming formalism. So that's also something we'll have to deal with. And the way we can do that, there's essentially two main aspects we need to, or two main approaches. Resolving this stoichiometric equality constraint that we have here can be done by essentially rewriting this equality into a sum of two inequalities. That for each flux, we have to satisfy both that a requirement that ax is less than 0, but then you could also you can turn that into an equality by saying that ax has to be greater than 0 as well, greater or equal than 0. If you were to double this up, but with opposed signs, then you would ostensibly have an equality requirement. So, yeah. Let's actually go into this and show how this is done in practice, because that's probably easier to see how that works then. So, here is our original metabolic model and the constraints that we have imposed upon it. Very simple as per usual. We import A through a reversible reaction. A is converted into B, which is then by a unidirectional reaction. B is converted to C by a reversible reaction, and then C is exported through a one-directional reaction. And here we have our bounds, which are very typical for what we'll see. We'll see like V1 has de facto unlimited excretion, but a limited intake capability. V2 it has to be less than 0, of course, because it's unidirectional. You have an implied greater than 0 on the left-hand side. Similar for V4, while V3, since it's an internal reaction, is effectively unconstrained on each side. I've put this minus 900 here instead of 1000, just to show later, for the sake of our, just to be able to contrast things later. So this is our stoichiometric matrix that corresponds to this. And right, so here we have our first row. Our first row is metabolite A. Our first column is reaction 1, reaction 2, reaction 3, reaction 4, and our rows are metabolites A, B, and C. And this is something we're going to have to convert into something that can be used by a linear programming framework. And so that, in order to do that, we need to do two things. The first is, because we have this requirement that each flux has to be positive, we have to split our reversible reactions, R1 and R3, into two different reactions. One which is the original, and then the other which is the same but reversed. So instead of saying that that A can be negative, we're going to say, that V1 can be negative. We're going to force V1 to be positive, but we're going to add a secondary reaction, which is V1R, which is the same as A, as R1, but is converted the other way around. It is turned around in direction. And we can show this by adding another row here. By adding another variable here in our v matrix or in our v vector, which will correspond to another column in our A matrix. Or yeah, so essentially here we have this column here corresponding to our normal v1, and then we have our column 2, which is v1r, which is the same, just with the signs reversed. And that means that that any negative effective flux through R1 is represented by the fact that we would have a V1R that is greater than V1. You can have both of these be non-zero at the given time, but the net effective flux through our reaction 1 would be represented by the difference between these two. And so whatever software we have that converts our metabolic model into a linear program, we'll have to do that conversion, but it's pretty straightforward to just keep track of what are our virtual reactions that are supposed to represent bidirectional fluxes, and then just undo those after we've processed our linear program. Similarly here, we see V3, which would normally be this row here. See 0 minus 1, 1. That corresponds to this row here. That corresponds to this row here. And we've had to add a V3R that is the same as V3, but just with the signs flipped, as we did here with V1 and V1R. So that's the first modification we need to do, because we need to satisfy this thing that all of these individual fluxes here are positive. But you also see here that we have twice as many rows, right? We have in our stoichiometric matrix, we only have one row, or we have 3 rows. We have 1 row for each metabolite. Here we have 6 rows. But what you'll see is that, as with these reversible reactions, here each row comes in pairs, where the second line, or the second row in that pair, is the one above it, but again reversed in sign. And this is because we have this equality constraint in our stoichiometric model. But we want our linear program to have an inequality constraint. So essentially the way we represent this equality constraint is we double up, or we add. An equality constraint is represented as 2 equality constraints with reversed signs. So this upper here will forces. Let's return a little bit. This upper bound here, or sorry, this upper row here represents that that you have to be less or equal to 0, while this lower here represented that you have to be greater or equal to 0. Combined, the only compatible solution is that the net production of that metabolite is 0, right? That's what you get if you combine it. Greater than equal. If x has to be greater or equal to A, and x also has to be lesser or equal to B, and minus x has to be greater or equal to B, then x has to be equal to B. And yeah, that's actually the second thing we should note here, is that if we return for a little bit here, our constraints are AX less than B. So the way and since what we're doing to put an equal constraint on it is that we're sandwiching it between a less than equal to b and a greater or equal to b. And that is done simply by reversing the signs on the row. So if we're saying that v1 minus v2 minus v3 has to be less than something, if we want to say that v1 minus v2 minus v3 has to be greater than something, then we can just say that minus this over here has to be greater, has to be less than whatever value we have. Essentially, by reversing the signs here in this row, we are reversing the sign on the constraint. So that is our first set of constraints. This is how we represent this stoichiometric matrix set of constraints into a linear program. But stoichiometric matrix is not the only constraint that we have. We also have the bounds on each individual flux. And so with that, the problem we have is that these aren't part of the stoichiometric matrix. Now we would think maybe this could be represented with this x through this constraint vector with x greater than 0, but this doesn't set any upper bound. Instead, we're actually going to have to squeeze our flux constraints here into our A matrix as well. But that is pretty straightforward. We can do that by just adding an identity matrix here, and then for each reaction, since we already have the implied constraint that these fluxes here all have to be positive, we only have to set an upper bound on each, which means that, so for instance, if v1 is between, if our real v1 is between minus 10 and 1000, since v1, our virtual v1 here, is unidirectional, we can set this to be bounded at less than 1000. It's going to necessarily be positive, and then v1r has to be less or less than 10. So we essentially what we do is we take our modified stoichiometric matrix, which is built by doubling up the rows in order to account for the signs, or for the equality constraint, that we have an equality constraint, not an inequality constraint, and for which we've added the columns representing to the reactions that we've had to add a reverse for. That's this blue part here, which is obtained from processing the stoichiometric matrix. And at the bottom of it, we add this red part here, which corresponds to the constraints. And then we have something something like this. Now I actually sort of messed up here. We're supposed to have 6 blue elements here because we have 6 rows of blue constraints. Here I accidentally only added a B row for the original stoichiometric matrix, but we should have 6 elements here. And these all have to be 0, right? So v1 minus v1r minus v2 minus 0 v3 minus, we can disregard those, but I mean they're technically part of the equation, has to be less than 0. Minus v1 plus v1r plus v2 blah blah also has to be less than 0. Those two requirements combined means that v1 plus minus v1r minus v2 has to be equal to 0. That's how we're doing that. That fits into these sort of blue set of constraints here. Well, this lower half here shows us v1 has to like virtual v1 has to be less than 10. Actually, I should have changed the order of these. But yeah, that it doesn't really matter. We would get the same here. We could just switch the nomenclature here. Similarly, v1r has to be less than 1,000. v2 has to be less than 1,000. And here we see that v3 has to be less than 1,000, with v3r being less than 900. And that's how we actually represent this basic basic metabolic model with just these reactions and these bounds as an actual linear program in a strict form. So our A matrix is not going to be just simply the stoichiometric matrix. It's going to have one part that corresponds to the stoichiometric matrix, but that needs to be extended in order to be compatible with the formalism of linear programming. And then we're also going to have to add a whole second part to this A matrix that corresponds to the constraints on both our original reactions in terms of putting the bounds about or positive bounds, and also adding while also adding additional constraints for the negatives as well, which is typically done by these virtual reversible reactions and putting an upper bound on those in case that the lower bound is negative. Okay, so or essentially for the lower bound in general. For unidirectional reactions with zero lower bounds, we don't have to add a secondary virtual reaction, simply because the requirement that each flux is positive is already implied in the linear programming formalism. And so this here is the actual linear program for basic FBA. But what we're seeing here is that we can actually add rows here, right? Each row essentially corresponds to a new constraint. And what we can do is we can add rows that represent whatever other requirements our model needs to satisfy. And so because of that, we have an actually pretty flexible system, right? So yeah, just to summarize, any constraint that we have that can be related to a linear sum of reactions can be added to our A matrix, right? The original ones are mass balance, steady state, and individual flux bounds, but we could conceivably invent some others. And the second thing that's important to remember is that equality constraints are a sum of two inequality sums, one with reversed signs. On top of this, I could also have added there that our AX less than B is like formula here. That is how it has to be formulated, but any greater or equal, any greater than equality can simply be represented by adding a row with reversed signs. And so in order to make an equality, we can do one greater than inequality and one or greater or equal, and then one lesser or equal equality. Those two combined, those two inequalities combined correspond to just simple equality. That's how we would represent that. So how can we use this? Well, let's talk about enzymatic constraints. And so in a cell, most reactions will not happen spontaneously, at least not at a biologically useful rate. They depend on some enzyme being present. And nominally, a higher amount of enzyme allows for a higher flux rate for whatever flux is being catalyzed by that enzyme. Not every enzyme will have the same efficiency, and also just because you have a lot of an enzyme present doesn't mean that the flux has to be high. It simply says, it simply allows for the flux to reach that upper bound. And so we can rephrase this variable efficiency, as well as the fact that the amount of enzyme really just sets an upper bound and not a lower bound on each flux, as this inequality here, that for enzyme I, we'll have GI, which is the concentration of that enzyme, or the amount of that enzyme present. Kcat will be the relative efficiency of that enzyme. Some enzymes will be able to catalyze quite a lot of flux for a low total mass of enzyme, while other enzymes will need to be present in much higher doses for a corresponding amount of flux. And so the product of the concentration multiplied by the efficiency will set an upper bound for the flux for the rate of reaction. And we can rewrite this by simply just shifting this kcat under here as, we can rewrite it this way. It's really just a very straightforward conversion. Now, in addition to this fact that we have a constraint on individual fluxes based on the amount of enzyme for that flux being present, the total amount of enzyme in the cell is also limited, because an enzyme has mass, it has a certain extent of volume, and you can't have an infinite amount of enzyme in a real cell, which is going to be finite in both spatial extension and also mass. And so essentially that means that the sum over all enzymes of the concentration of that enzyme multiplied by the molecular weight of that enzyme has to be less than this constant P, which is the total enzymatic capacity of the cell. So what happens if you combine these two constraints together is you get the following. Is essentially that the sum of flux multiplied by the molecular weight divided by the efficiency of the enzyme has to be less than the total enzymatic capacity of the cell. And this here is essentially a linear constraint, right? So this would be, we could represent this by a row in our A matrix, where each column entry into that row is this MWI divided by kcat I, and that this has to be less than P. So this would just add a new entry at the bottom of our B vector, while this would just be another entry at another row at the bottom of our A matrix. And this is we could just add that pretty straightforwardly. And I'm going to show how we would do that in a couple of slides. But this formalism here only really applies for the simplest case where there isn't a one-to-one correspondence between enzymes and reactions. In reality, it's not that simple, of course, because often a single reaction will be catalyzed by one or several enzymes, by either a combination of enzymes, a complex where everything has to be present, or you can also have isozymes where the upper bound on a given reaction is not given by a single enzyme, but by the sum of two enzymes present. And that's essentially how we would represent this, right? So for an isozyme, that's the upper row here, then the upper bound on the associated flux has to be less, or is that the flux has to be less or equal to the kcats multiplied by the sum of the enzymes. Meanwhile, for complexes, you need at least both. You're essentially for a complex, you're constrained by whichever enzyme is, or like partial enzyme is present in the lesser amount. So that has to be, that we phrase this as Vj less or equal than kcat multiplied by the minimum of our enzymatic concentrations. Now, this upper part here with isozymes is actually pretty straightforward, because here we simply have this is a very simple linear inequality. We have one variable has to be less than the sum of two others, while on the bottom here it's worse, because this is not a linear relationship, but it can be adjusted, and we're going to show you in the next slides how we can do that. So in order to deal with this notion of enzymatic constraints, we add auxiliary variables. So here we have, imagine we have an isozyme. We have reaction V1 that has that is catalyzed by enzymes G1 and G2. And so our constraint is that V1 has to be less than G1 plus G2. And that we're just assuming all our kcats are 1 for simplicity. So all our entries here are going to be 1. They don't have to be, but it's more compact to just assume that all our kcats are 1. So if we say that V1 has to be less than G1 plus G2, that is the same as saying V1 minus G1 minus G2 is less than 0. If V1 minus G1 minus G2 is negative, then then that means that V1 is less than G1 plus G2. And so we've essentially added that enzymatic constraint based on isozymes by adding two auxiliary variables into our flux vector, and then adding an additional constraint associated with it. So that's an example of a single enzymatic constraint represented. Of course, if we just had V1 represented by G1 alone and there was no G2, that it was just like a simple one-to-one relationship, we would just not have this column here, and we just have to say V1 minus G1 less than 0, or less or equal to 0, and this would still be valid. How can we use this for enzymatic complexes? Well, imagine now that we have V1 instead catalyzed by the isozyme G1 and G2. What we can do then is we can add a third auxiliary variable corresponding to that isozyme, which we'll just call G12. And what we'll say is that the flux through V1 has to be less than the concentration of G12, which we do by adding this line here, which just V1 minus G12 less than 0. While similarly, we say that G12 has to be less than both the concentration of G1 and the concentration of G2. And those are two individual constraints. So, and so that will give us two rows in our at the bottom of our constraint vector, or sorry, of our constraint matrix. So this row here, third from bottom, consists of minus G1 plus G12 being negative, which means that G1 is less. That G1 is greater than G12, and the requirement that G12 is also less than G2 is represented by the same, just with another element, like with an element here corresponding to minus G2 instead of the element corresponding to minus G1. So these two rows in combination here gives an upper bound for G12. This is the way we represent that G12 is at most the minimum of G1 and G2. So that is done by these two rows here. And so these three rows in combination essentially forces V1 to be both less than G1 and less than G2 at the same time, and represents the mechanics of an isozyme. Now lastly, as we started off by saying, enzymatic constraints come in two levels. The first is that each enzyme or complex imposes a limit on individual fluxes, which we've seen through that we represent through these three rows here. But the second part of enzymatic constraints is that the total amount of enzyme in the cell is constrained. And that we can represent by, again, adding just another row here. And so since we consider that G12, that's a complex that is simply assembled at a given time from the amount of G1 and G2 present in the cell, it's the formation of G12 is not going to crowd up the cell any more than the than is already done by the G1 and G2 that's present in it. So essentially our enzymatic constraints here is that G1 plus G2 has to be less than P. And so we do that simply by adding a row at the bottom here where we say G1 plus G2 less than P. Again, G12 does not enter into this because G12 is already limited to be less than both G1 and G2 individually, and for whatever reaction or for whatever flux regulation that we'll have, when G1 and G2 combine to form G12, they are not going to crowd up the cell any more than what we already have. And so that is how you would add some simple enzymatic constraints to a model. First you add some rows representing, so this first row here represents essentially the constraints on the reactions. Again, I could maybe have made a sort of barrier here showing that our left columns here correspond to limitations on the flux rates, because our first rows here are flux variables while our lower rows are enzymatic variables. That similarly means that our leftmost columns are flux variables and our rightmost columns are enzymatic concentration variables. And so first you add some rows in your A matrix that represent the constraints imposed on fluxes by enzymatic concentrations. Then you can add rows representing relationship constraints that the various enzymes impose on each other. Typically, again, that our virtual complexes here are limited by the concentration of its constituents, and that will correspond to these middle two rows here. And then we add a bottom row that corresponds to this total molecular crowding constraint. And so, yeah, to summarize topics of today, is that we've seen that the linear programming backend, so to speak, like the technical, like under the hood formalism of how this is solved, requires typically a very specific format for how things are written. And it seems maybe a bit restrictive at first and a bit complicated, but it is in fact quite flexible. It is not too hard to rewrite most deviations from the formal requirements in order to be compatible with what we actually have, right? And the fact that the formalism requires that everything is a less than inequality is not really a problem. It doesn't prevent us from actually representing requirements that in real life are greater than or equal to, for instance. And so, because of this flexibility, we can actually add a lot of constraints to our model that aren't just simple stoichiometric constraints. In some cases, though, we will need to add certain auxiliary variables to allow us to represent constraints, whether for enzymes individually, but also how to represent the internal or the constraints between between enzyme complexes and individual enzymes and their concentrations. And essentially, yes, enzymatic constraints are a very good example on how we can extend linear programs to represent various types of constraints, because enzymatic constraints typically fit quite nicely into this linear framework. There's certainly other constraints that you might want to add that maybe don't correspond to linear or to restrictions on linear sums of fluxes or of whatever other auxiliary variables you would include, and then this reasonably simple framework that we have here doesn't apply in the same way. I'm not going to say that there aren't ways to handle that, but that would fall outside the scope of this class. And even then, if you can solve it, as we know, nonlinear programs typically tend to run quite a lot slower than linear programs in any case. But anyway, even then, like just being restricted to linear linear extensions of FBA, we can add quite a bit of interesting things. So I think we can wrap it up there for today, and this will actually be the last like proper lecture of this class. I think that I'm going to put some other videos up until maybe like the end of next week, so there would be 3 more, maybe less than that, maybe just 2, depending a little bit on how much I could fit into each of them. But the idea for those is that I would maybe be going through certain exercise sets, maybe from earlier exams, and show and practice a little bit what you can expect on the exam and how you can actually solve some of these problems in an applied situation. Thank you.